Thank you so much, everyone, for coming to the session. I'm Nikhil Shivakumar Nayak. I'm a principal research scientist in the Red Hat AI innovation team. I've been working on parameter efficient learning, continual learning, reasoning in language models. And today I'll be talking about continual post training in large language models. Specifically, I'll be talking about our recent paper that came out like a few months ago. It's called Sculpting Subspaces, Constrained Full Fine Tuning in Language Models for Continual Learning. Thank you to my co-authors, and we have a paper, blog, and code if you want to play with some of the experiments in the paper. So what does the current post-training regime look like? So after a model is pre-trained on a large corpora of text, there are many stages that happen during post-training. The first stage is fine-tuning, where you have like a domain-specific data set where you want the model to specialize in that domain, or maybe you want the model to remain general, but you want it to follow instructions well. So that stage is usually called supervised fine-tuning. And then there's the alignment stage, during which preference tuning happens, and there's safety and values alignment. This usually happens using reinforcement learning. Followed by more recently, a lot of people are interested in improving the reasoning of language models. So there's a specific stage only for improving the reasoning using reinforcement learning again. And then finally, you want the model to be efficient. So you do model compression techniques and knowledge distillation for a small model. So the problem with this sequential setup is that as you maybe teach the model to be aligned with human values, it can forget the domain-specific knowledge that it learned during the previous stage. So as you go on fine-tuning on each stage induces forgetting of previously learned capabilities and knowledge. So this problem is very well known in the literature, and it's called catastrophic forgetting. And the problem of catastrophic forgetting mainly has like three drawbacks. So the first is knowledge degradation. Whenever you learn something new, everything that was learned before is forgotten, and this creates a significant challenge in the language model lifecycle. Second is scale intensifies forgetting. So as you move to bigger models, for example, from Llama 3B to Llama 7B, forgetting actually increases as you learn new tasks. Finally, resource wastage. If you want the model to know everything that you have taught it so far, then this can, retraining the model on everything can cost millions of dollars in compute resources. So what is the impact of catastrophic forgetting? So you can see on the plot in the left, as language models learn more, that is, as your green bar becomes bigger, your orange bar also becomes bigger. So as your language models learn more, they also forget more. And you can see, for example, in the Llama 3 8B model, there's more learning, but also there's more forgetting. And there's extensive research that shows that models lose up to 40% of the previously acquired capabilities. So how do we mitigate catastrophic forgetting? There are mainly three buckets in terms of how people in research have approached this problem. The first is regularization and memory-based methods. So here you have like a replay buffer that has everything that was learned before, and using these replay buffer, you try to reinforce the knowledge. Second is regularization, where maybe you try to identify the important parameters in the model and try not to change it. The second is parameter efficient and subspace approaches, where you fine-tune only a subset of the parameters and not the entire model. This reduces forgetting, but at the same time, your model isn't as expressive as it was before because you're not reusing all the parameters in the model. The third bucket is model fusion and modular architectures, where you maintain like separate model copies for each new specialized task that you're trying to learn. But again, this increases the model size. So each approach has their own unique trade-offs between performance, memory, and computational efficiency. So let's dive a little bit more into detail for each of the buckets. So in replay buffer, again, the advantage is you reinforce prior knowledge using replay buffers, but the problem is you need large storage for storing all the data that the model learned before. And it also increases compute, and it may raise privacy concerns because you might not be able to store the data from before for a long period of time. And access to past fine-tuning data or pre-training data is not always available. For example, if you take a model from Hugging Face like Llama, you don't have access to the instruction tuning data that it was trained on. So it's not possible to always have a replay buffer from the task that was learned. Then in regularization, you have gradient projection methods. It prevents overwriting of critical representations. But again, this is not always effective in like every scenario because it's really hard to identify the critical parameters for a given task. Then the third bucket is second bucket is parameter efficient and subspace approaches. Here the advantage is again, it's lightweight and you only fine tune a subset of the parameters, so it forgets less. But the limitation is that it limits expressivity. A variation of LoRa, which is the current state of the art called orthogonal LoRa, it ensures the LoRa updates are in a subspace that's orthogonal to the previous task. This minimizes interference between the task-specific LoRa adapters, but the limitation is, again, it restricts learning capacity. The final bucket is model fusion and modular architectures. So in model merging, what you do is, let's say you have n tasks, you train a separate model on each of those n tasks, and then post hoc you try to merge them. This retains diverse task knowledge, but the limitation is that, for example, if you have two models that have like conflicting representations, it's very difficult to find a post hoc way that works in order to like restore the capabilities of both the tasks because they have conflicting representations. And then you have mixture of experts model where you have a different expert for each new task. And the advantage is that you're not changing any of these experts. So it mitigates forgetting by isolating learning. But the limitation is that the model size is increased. So if you have n tasks, you have parameters that are worth like n times the original model size. And then there's routing complexity because during inference, as you get new queries, you don't know which expert model should handle that query. So there's routing complexity. So yeah, these are the problems. So what if we could have it all? The first is if minimize catastrophic forgetting so that the model retains critical knowledge from previous tasks. There's uncompromised expressivity, same as full fine tuning, where you're reusing all the model parameters to learn the new task. And then you want to be parameter efficient. You don't want to introduce new parameters like LoRa. And there's no need of historical data. You don't want to store the data from before either due to privacy concerns or because it's expensive to retrain. So what is the solution? The solution is constrained full fine tuning. So let's take a step back. What does LoRa exactly do? So LoRa performs low rank updates. The delta W is the update to the weight parameters, and it's of the form A times B, where A is a matrix of size D cross R, and B is a matrix of size R cross K, where R is much, much smaller than D and K. So this is parameter efficient. It reduces training, but still introduces task-specific parameters. What do we want to do better than LoRa? We want to do these low-rank updates in the subspace that the model parameter is already in without introducing new parameters. So there's a paper called Laser, and Laser, what they show is that they do a singular value decomposition of each weight matrix in the model. And these singular vectors, what they are is, if you look at the singular vectors corresponding to the high singular values, these are the vectors that encode important information. And then singular values that are low, the vectors corresponding to that, represent noise or redundant information. So Laser, they do a singular value decomposition, and then they discard these low singular values using a threshold. And even without fine-tuning, they show that this gives improved performance on the task that they're concerned with. So this is like an illustrative diagram where you have each weight matrix, and each weight matrix goes under singular value decomposition, where you have U, sigma, and V matrices. And for each of these matrices, you only retain parts of the model. You throw the parts that correspond to noise or redundant information, which is high-frequency components. And without training, they show like improved performance. So this diagram basically shows the different types of matrices. For example, you have the attention key, attention query value, and the MLP input and output matrices. And you have different reduction percentages. So the dark color, which is 99.75% reduction, which means you throw away 99.75% of the weight matrix. And they show that performance on the task, in fact, improves. So on the y-axis is loss. The dashed line is the baseline model. And you can see that in some cases, even with 99.75% reduction, the performance, the loss value is actually below the baseline. Right? And we wanted to see if this also works in models that we are concerned with, for example, in Granite 8B. And we evaluated this on Leaderboard, which is a benchmark that has 6 tasks. And we did similar reduction. For example, we did 90% reduction, and we saw that across these benchmarks, performance is actually retained. So building on top of Laser, Spectrum, what they do is, again, they do a singular value decomposition, and they find the matrices that have high signal to noise ratio. What does that mean? What does high signal to noise ratio mean? So using random matrix theory, they find threshold for each of these individual matrices, and all the singular values that are above this threshold correspond to signal, and all the singular values below this threshold correspond to noise. So they take a signal to noise ratio, and then they only fine tune the top 25% of the weight matrices that have the highest SNR. So similar to the previous paper where they just discarded the high order components or the low singular values, here they target the matrices that have high signal to noise ratio. And they retrain only top 25% of the layers with highest SNR. This is obviously parameter efficient, so you can see the memory savings and training time. So for example, in distributed training settings where full fine tuning takes peak memory usage of 24.92 gigabytes, just retraining 25% of the layers that have the highest signal to noise ratio uses 19.18 GB. So it's 23.05% more efficient, and also has much less training time. And it can be combined with other complementary techniques like quantized LoRa to get even further gains. Okay, again, so taking a step back, so what is the problem setup? So you have these model parameters. Let's say you have L layers, and each layer has a matrix W. And each layer is of dimension D0 cross Di, and it can contain millions of parameters. For example, Llama 2 7B has, for each weight matrix, it has millions of parameters. And tasks arrive sequentially. So you have capital T number of tasks, and the goal is to learn each task small t while preserving the performance on all the tasks that came before, because maybe you don't have access to the tasks that came before, or it might be too expensive to learn all the tasks from scratch. So this is the problem setup. So what's the first step in our methodology? The first step is again doing a singular value decomposition and then identifying low rank and high rank subspaces. So what does low rank mean? You want to find a subspace that is important to the model, which is the high rank subspace, and the part of the model that you want to fine tune is the low rank subspace. How do we identify this? So one of the core assumptions for our method is that the data or the tasks that were learned up until now reside in a subspace that is spanned by these high singular vectors. And this is a reasonable assumption to make because, for example, if you train a linear layer, that's just like one MLP layer. If you train that layer on a data set, after training, it ends up in the direction that spans the maximum variance in the data. So this is also empirically seen. So if you look at the plot here, on the x-axis is all the singular vectors, and the leftmost are the singular vectors corresponding to the highest singular values. So you can see the matrix vector product. If you look at the L2 norm of that, you can see that the data mostly resides in the subspace spanned by these high vectors. So for like the first few, it peaks and everything else is close to zero, which means you can change those parts of the matrix without affecting the performance on the previous task. Okay, so how do we determine layer importance? We know that we can do low rank approximation of these matrices, but we need a way to identify how important each layer is. So inspired by another paper called Adaptive SVD, the importance score that we compute is using the cosine similarity between the input and the output activations. So high similarity, that is if xi and yi are very close to each other, it means the layer is preserving the input directions. And it encodes task general features that we need to retain, right? And if it's like, if the cosine similarity is low, it's something that you can change without affecting the performance on the previous task. And these scores are normalized across layers. Okay, so now that we have the importance score from the previous slide, we introduced two new hyperparameters, the minimum retention ratio and the target retention ratio. Minimum retention ratio basically tells you for the least important weight matrices in the model, how much of the matrix should I retain? And target retention ratio basically says for weight matrices that are super important, how much of the model do we want to retain? So these two are hyperparameters. So for example, the final retention ratio that is computed is using these two hyperparameters and the importance score that we got from the previous slide. So for example, if let's say the importance score for a given matrix is 0, then the retention ratio is exactly the minimum retention ratio. And let's say the weight matrix is super important, which means the importance score is 1. Then in that case, retention ratio becomes the target retention ratio. So empirically, we set it to TRR as 0.8 and MRR as 0.4 in our experiments. So based on these retention ratio, we basically split a weight matrix into two parts, the high rank subspace and the low rank subspace. Yeah, and we also explored different effective rank approximation methods. One is what Laser does, where they use just a static value R for all the weight matrices in the model. But this results in suboptimal retention adaptation trade-offs because for both layers that are important and that are not important, you're using the same effective rank. Spectrum uses random matrix theory, and they use values from a Marchenko-Pastor distribution. But this distribution basically assumes that all the elements in the matrix are independent and identically distributed. But this is not the case, especially when you're learning data with large language models. The elements in a weight matrix are actually correlated with each other. The third thing we looked at is Shannon's entropy of the spectral values or the eigenvalues in a matrix. One thing that works surprisingly well is allocating a predetermined budget. So for example, if you have n tasks, for the first task, you train the entire matrix. For example, if you have 5 tasks, for the first task, you train 100% of the model. For the second task, you train 80%. For the third task, 60%, and so on. And this and allocating a predetermined budget works surprisingly well in practice. And we did some analysis on the singular value statistics. For example, if you look at the leftmost plot, the key projection matrix, you can see that, for example, for layers 20 and like 30, all the singular values are close to 0, which means the effective rank of this matrix is very low. And you can reuse the entire matrix. But for example, in like the up projection matrix, which is an MLP layer, if you look at maybe layers between 15 and 20, there's a good distribution of singular values. So maybe you want to retain only the highest singular values in that scenario. Okay, so now that we have bifurcated each matrix into the high rank subspace and the low rank subspace, how do we actually train the low rank subspace? So we do this using projected gradient descent. So the high rank subspace is kept frozen. For the low rank subspace, you take the gradient of the loss with respect to that low rank subspace, but you ensure that it doesn't come in the way of the high rank subspace. And the way we do that is using projected gradient descent. So for each gradient that you get for the low rank parameters, you subtract the components away that lie in the subspace spanned by the high singular vectors, which is the projection step after each gradient. And this promotes knowledge retention while allowing effective task-specific adaptation. This is the algorithm summary. I won't go over it again. And this is an illustrated. I think this would be a little more intuitive to look at. So you have, on the leftmost is a transformer language model that has many layers. Each layer goes through a computation of layer importance, which is normalized. And then using the minimum retention ratio and target retention ratio on the top, which are the two hyperparameters, you do a singular value decomposition, and then you split each matrix into the high rank subspace and the low rank subspace, right? And then you have these tasks that are arriving sequentially. And for example, let's say we're trying to learn task I, if you see the top right, and task I minus 1 is something that you have recently learned, and maybe there's a shared subspace between the two, and you don't want to fine tune in that subspace. So the gradient projection step that I showed in the earlier slide basically takes that subspace away, and the only thing that you learn, or the subspace that you learn in, is the new task subspace without the shared span after the gradient projection step. Okay, so finally coming to results, we have two standard continual learning benchmarks that we looked at. Most of the tasks in these standard continual learning benchmarks are classification and natural language inference tasks. And these are quite complex because the number of classes in each of these tasks is like 15 to 20. So you have the 5 task sequence and the 15 task sequence. So the way it's evaluated is you'll learn each task in a sequence, one after the other. And then finally, you compute the average accuracy. So after learning the final task, you compute the average accuracy over all the tasks in the sequence. And this is evaluated using two models, T5 large, which is an encoder-decoder model, and Llama 2 7B, which is a decoder-only model. And you compute the average accuracy. And results are averaged over 3 random permutation of the task sequences in order to ensure that the results are robust. And we compare to current state of the art, including orthogonal LoRa. And these are the baseline methods that we compare to. So the first is sequential fine-tuning, which is a lower bound baseline because it is very prone to catastrophic forgetting. So even though it can learn this new task very well, it forgets everything that was learned before. And then you have parameter efficient LoRa, including different variants like sequential LoRa, incremental LoRa, and the recent state of the art orthogonal LoRa that we spoke about earlier. And then you have the replay-based approaches using standard replay buffers from prior tasks or knowledge. And then you have regularization methods. Again, these methods identify important parameters for previous tasks and make sure that you penalize or at least don't change them as much. And then you have prompt-based techniques. These, for example, progressive prompt attaches a new prompt for each new task. So it uses a different prompt for every task. So this is, in essence, like using like different models because you're using different prompts with each task. And during inference, the challenge is how do you identify for the question, how do you identify which task it comes from and using the prompt according to that. And then there are a couple of model merging techniques that we compare to slurp and ties. Slurp is full model merge. So it trains like separate models for each task and then does full model merge. And ties is LoRa adapter merge. So it trains a LoRa adapter for each task and then merges that. And then we have uh, two methods that kind of are the upper bound. So per task FT is you train a full model for each new task and then you just compute the accuracy. So it ensures that there's no overlap between, there's no forgetting because you're using, for example, if you have n tasks, you're using n different models to learn those tasks. And during inference or while computing average accuracy, you just use the model that corresponds to the task. And multitask learning, it relaxes the continual learning constraints because it makes an assumption that all the tasks in the sequence are available in the beginning and you can just train on all of them together. And this helps with like shared task representation. So this is kind of the upper bound per task FT and multitask learning that we compare to. And these are the methods. So on T5 large, using both the 5 task and 15 task standard continual learning benchmarks, you can see that our method outperforms all the LoRa baselines and the regularization based baselines, as well as the model merging techniques. Yeah, there's a partition in the table because in the bottommost are models that aren't really a fair comparison because either they have additional parameters for each new task or they're assuming or they're relaxing the continual learning constraint where they train on everything at once. And then we also did a couple of ablation studies to understand like what parts of our methodology is actually important. As you can see, the average accuracy with Llama 2 7B, the first row in the second table is 79.6. This is again 3 points higher than the current state of the art orthogonal LoRa. And one of the ablation studies we did is what happens if you half the value of the minimum retention ratio and the target retention ratio. This means that the effective rank, you do a more aggressive approximation of the effective rank, which means for the new task that you're trying to learn, you have a bigger part of the model that you're using. And this, of course, leads to a lot of forgetting. As you can see, the average accuracy drops from 79.6 to 51.5. The other ablation study we did is while you're updating the low rank subspace, what happens if you don't do the gradient projection step? That is, you let the low rank, the vectors in the low rank subspace come in the subspace spanned by the high singular vectors. This, as you can see, again leads to a lot of forgetting because the high rank subspace is part of the model that you want to keep frozen so that you preserve the previous knowledge and capabilities of the model. As you can see, there's a big drop from 79.6 to 31.2 when you do unconstrained low rank updates. So we also evaluate on a benchmark called trace. This is a more realistic benchmark because these are the kind of tasks that you would see in the real world or in production. So they span domain-specific data sets, multilingual, mathematical reasoning, and code completion. So in total, there are 8 tasks in this benchmark. You sequentially train on each of these tasks, and then you evaluate it on all the tasks that you just trained, as well as you look at the general abilities of the model, the safety evaluation, and the instruction following. So these are capabilities of the model it learned during instruction tuning or fine tuning. And how does learning 8 new tasks on top of the instruction tune model, how does that affect general abilities, safety, and instruction following? Yeah, so these are on the left table one is the 8 tasks that we train on. So for example, science Q has science knowledge reasoning, and then there's a financial domain understanding data set. Then there's long context understanding, and there are a couple of multilingual data sets, Chinese and German. There's one code data set, and there are 2 numerical reasoning or arithmetic reasoning. And for the general abilities, we look at, for example, most of them are QA data sets. So you look at MMLU, which tests factual knowledge, and then there are 3 or 4 reasoning data sets. So you have general reasoning, mathematical reasoning, common sense reasoning, and reading comprehension. And we also have a multilingual data set. And to test the instruction following, has the model lost any of its instruction following capabilities? We test on 2 data sets, the self-instruct and Lima, which stands for less is more for alignment. And then there's one safety evaluation data set, Kona. Okay, so what are the 2 metrics that we look at? Here, we look at 2 metrics again. So the one from before, average accuracy. So you train on all the tasks, and then after learning the final task, you get the accuracy on all the tasks in the sequence. That's one. Then the second is backward transfer. This exactly quantifies how much catastrophic forgetting has happened, because the way it's computed is you look at the difference between when the model immediately learned the task and after the final task was learned. So when the model immediately learned the task is when it has its best performance on that specific task. And then you see how much of that accuracy has gone down after learning all the tasks in the sequence. So this exactly quantifies catastrophic forgetting, and you want this value to be low. And yeah, you can see the results. So our method achieves higher than current state of the art orthogonal LoRa by like 7 points, much bigger margin than before. And it has comparable backward transfer. So it is negative 7.1, whereas orthogonal LoRa is negative 6.2. Yeah, so this demonstrates our method's ability to effectively retain and transfer knowledge, and also in its robustness to forgetting. Okay, and these are results on general ability, instruction following, and safety. So if you look at the left plot, the last bar, which is the average of all the 6 benchmarks, you can see that this is compared to Llama 2 7B chat model, which is the base instruct model. So we are comparing to the original model after training on the 8 tasks, how much has the general abilities gone down. So you can see that on average, it's like about the same. It's only 0.6% lower. But two things to note here is that there is a significant drop in both GSM and BBH. And this is kind of expected because when you're learning new tasks, if learning of those new tasks is not augmented with reasoning traces, if you don't do reasoning augmented continual learning, which is adding like chain of thought reasoning before the answer, then benchmarks like math and reasoning take a big hit. And that's what has happened here. But if you include that, then you would see that even these benchmarks would retain performance. And then on the right is instruction following and safety. Again, this is compared to the base instruct model, and this is evaluated using GPT-4o. So you give the response from both the instruct based model and from the model that was trained on the 8 tasks, and then you say, which of these two responses follows the instruction better, or which of these answers follows safety better and doesn't have any harmful language or words in the answer. And you can see that for the other methods, for example, like replay buffer and LoRa sequential fine-tuning and sequential fine-tuning, there's significant drop in both the helpfulness and the safety capabilities of the model. But our model, in fact, is like better than the base instruct model. So you can see that it wins 24 times, loses only 20 times in instruction following, and there's a tie 56 times. Similarly, for safety, it wins 18 times, loses only 4 times, and tie is 78. So it's, in fact, better than the base instruct model. Yeah, so towards the utopia of continual learning, so what's the vision? Our vision is basically where models can learn continuously with near zero catastrophic forgetting. And the real world goals are robust performance on tasks like quality, and which is long form question answers and reasoning. And these are some of the limitations of our current work. So it's, as you can see, as I said earlier, during the ablation study, our method is very rank sensitive. So if you use like half the value for the hyperparameters TRR and MRR, there's a significant drop. So we need more principled and data-driven methods to determine the effective rank for each matrix in the model. Second is dynamic allocation as you scale the task horizon. So if, let's say if you have 20 tasks, then you want to be able to dynamically allocate parts of the model to each of these tasks. And then the SVD overhead. So you do the singular value decomposition once before training on each new task. And it's a minimal overhead, but it would reduce even further if you do it for specific matrices and keep other matrices. For example, if you keep the MLP matrices frozen and you only do SVD or training on the attention matrices, this could further improve efficiency. Yeah, that's it. Thank you for listening, and happy to take questions.